Conservation of mass. I believe we introduced the concept of conservation of mass in one of the earlier chapters. When you have a reaction occurring like burning wood, you don't actually destroy any of the matter. You're just changing it into a different form. So matter is neither created nor destroyed in a chemical reaction. Chemical reaction, as opposed to a nuclear reaction. In a nuclear reaction, you can have significant changes in mass, but not in a chemical reaction. So what we observe is both during physical changes and chemical changes, the total amount of matter remains constant. Now, when you burn a log on the fireplace, if you don't capture the gases that are given off, it may appear to lose mass, right? The ashes weigh a lot less than the piece of wood did. But we're not accounting for the products of that reaction, the carbon dioxide and water vapor that escaped. If we do it in a closed container, we find that mass is indeed conserved. So if we were to burn 58 grams of butane in a lighter, it would react with 208 grams of oxygen. And you are just being told those numbers. Okay, they're not coming from any particular thing. But if you have 58 grams of butane and it reacts with 208 grams of oxygen, your total mass of things reacting is 266 grams. It's just these two numbers added together. They produce carbon dioxide and water. They will make 176 grams of carbon dioxide and 90 grams of water, because I said so at this point. If we add those things together, we'll get 266 grams. This is a chemical change. The butane has been destroyed. The oxygen has been destroyed. We have formed two new substances, but the mass of them is the same. If you take a Lego car and a Lego tree, and you take the blocks apart and you make them into a house, and you use all the blocks, does the house weigh more or less than the car and tree together? It weighs the same, because you have the same number of each kind of brick, right? Lego blocks do not disappear into thin air. Sometimes when you're looking for that one special piece, it seems like they did, but it's actually under the couch, or the dog ate it. That happens too. Lego bricks don't disappear into thin air, and they don't appear out of nowhere, right? Atoms can't appear and disappear either. However many atoms you have to start with, you have to end up with. And so the mass of all the products together is the same as the mass of all the reactants together. And that's a very important concept. Now, especially if you've had chemistry before, it's easy to take an example problem like this and make it harder than it needs to be. So let's try not to overthink this. Suppose 12 grams of natural gas combines with 48 grams of oxygen in a flame. The chemical change produces 33 grams of carbon dioxide. How many grams of water form? So they are giving us the names of the reactants and products. What are the two things that are reacting, that are burning? The natural gas and the oxygen. Those are burning, and what are they forming? Carbon dioxide and water. Okay, they told us how many grams of gas. 12 grams of natural gas, and it's reacting with 48 grams of oxygen. If we add those together, we get 60 grams, right? And it says it makes 33 grams of carbon dioxide. How many grams of water? We started out with 60 grams. We have to end up with 60 grams. 33 of it became carbon dioxide. The rest of it has to be water. 60 minus 33, 27 grams. Okay? This is equivalent to a problem like George brought 12 cookies to the potluck, and Otis brought 48 cookies to the potluck. And Charlie took 33 cookies. How many did Walter get left with? How many cookies total were there? Charlie took some, and Walter got the rest of them. That's all it is.